Now we can also prove that because that this is I'm going to use change vector 2 variables now. Because the directional derivative towards direction u equals the gradient vector dot product with the direction, the dot product basically can be rewritten into this form, where theta represents the direction, the angle between these two vectors. So obviously we're going to have the gradient vector looking like this in some space, and then u is going to look like this in some space, and then this angle between them is going to be u. And we can infer that if cosine is 0, if the theta is 0, or 180 in this case, but let's just say 0, is that this is going to go to 1, and the directional derivative is simply going to be the two magnitudes of the vectors times 1. Obviously, when this goes to 180, it's going to be -1, so you have to add a negative symbol there, but we'll just, looking at pure magnitude right now, this is going to have the highest magnitude of every direction possible, because cosine of any other value is going to give something less than 1, because cosine goes to 0 to 1, looking at magnitude only. This is going to be when the directional derivative is the biggest. And just like a single variable calculus, the derivative, it basically gives us the rate of change, and so the directional derivatives gives us the rate of change in that direction for a function. And so what we can know is that since this is the largest when theta is 0, we can infer that the directional derivative is largest, and obviously the directional derivative is the rate of change in that direction, in the direction of the gradient vector. And this is useful for whenever questions that ask what is the greatest rate of change in a given place, and we would find that greatest change by simply setting the u direction as the gradient, but of course adjusted for magnitude and making it into a unit vector.